Hi everybody, this is Tor Storley, and I am back with another video. In this video, we're going to take a look at how you can create a graph SQL database in DuckDB. So first I want to introduce what a graph database is, and then we also look at who is using it and what are they using it for, so major companies and how they take advantage of graph SQL or graph database. We will look at some comparison between another database like SQL Server and how their structure is working versus what you find in DuckDB, for example. We'll look at the extensions we're going to be using, the DuckPGQ extension. We'll look at some of the sample examples that comes with that extension, and we also point out where you can find more information like a blog post, etc. And finally, then we want to set up some examples that demonstrates how to run these queries in DuckDB UI environment. So let's get started. So with a little help from my friend Claude Sonnet 4.5, I came up with this document here that demonstrates introduce, I should say, the graph database and what it is. I want to go through this document quick so you have a good background on what it means to have a graph database and how these structures work. So as you can see, I created this document. So let's just go through that quick. So what is a graph database? Well, a graph database is a type of database that uses graph structures to store, map, and query relationships between data. So unlike, for example, relational databases, they will store data in tables with rows and columns, and you set reference to the different tables via their relationships, such as primary keys and foreign keys. Now, as these relationships grows and all these links are getting more and more complex, it's very difficult to maintain these in a relational database because there becomes so much of it. If you look at the structure of a graph database here, you can see you create what is called an entity, such as, or node, I should say, like a person, for example. So here you get a person Alice, a person Bob, and a person Carol. And you also set up their relationships. These are called edges, okay? So how do you connect between them? For example, Alice is a friend of Bob. Bob is a friend of Carol. And it also goes both ways. You can say Bob is a friend of Alice. You can see here, what does Alice do? Well, she can purchase products like coffee. She can live in a city like Seattle. And you can see that you very soon start creating all these connectors and all these relationships between these nodes. Product is a node, person is a node, and then these are the edges or the connectors between them. So if you look at the legend here, you can see the blue one is a person node, the green one is a product node, and the orange one is a location node. And these are the relationship edges between these nodes. You can set up very, very complex relationships by using this structure. Okay, as you can see, the edges, which is the connectors, they can have properties that describe the nature and strength of the relationships. So therefore, that makes the graph database extremely powerful, modeling very complex interconnected data. You can imagine how many joins you will have to do in a relational database to once these relationships get more and more connected. Why should you use a graph database? Well, it's very intuitive as far as modeling it. It simplifies your queries, and the performance is obviously very good. The graph database or the graph query language provide visual declarative syntax that makes the complex relationship in the queries readable and maintainable, and reduces a lot of the clutter you will have, like if you were going to create this, like say with a recursive CTE, for example, like in DuckDB. Okay, you can read through this. I'm going to make this available on my GitHub repository so you can take a look at it yourself and read through in more details. Who is using it? Well, let's look at some of the bigger usage of this technology. LinkedIn, for example, uses this technology to power its professional network, including features like people you may know, calculating network sizes and connection strength, and identify true leaders and influencers within that industry. So it contains hundreds of millions of professionals and billions of connections. because each of these connections demonstrating a different connection between these people, for example. Facebook, or these days it's called Meta, you can see here it built its own graph database infrastructure to manage its massive social graph of billions of users and trillions of connections. Now try to set that up in a relational database. That would be impossible. Google, it uses it for its knowledge graph, as you can see here, and for question and answering scenarios. And you can see here, if you search for, say, Barack Obama, you're looking for information for the 44th president of the United States, and therefore you can surface related entities, like related nodes, like other persons, for example, like this. Financial institution, they look for fraud detection. E-commerce giants like Amazon and eBay, they can use it for product recommendation. They can analyze each individual and customers, what they buy and so forth, and suggest other products for them to purchase and other categories, etc. So that whole linking can get very complex. Telecommunication companies uses this. Healthcare organization, they use graph databases to model patients' care pathway, drug interaction, and disease progress patterns, so it enables better treatments and recommendations. And even NASA, as you can see here, uses this type of modeling for their missions and the spacecraft components and scientific data. Okay, so if you want to see kind of what SQL Server is doing, you can go to this page here on Microsoft's website, and I'll produce a link for you so you can find it. But as you can see here, this is how you create a graph database and run some pattern matching queries using T-SQL. So it goes through graph structure here, and it shows you some simple scripts. It shows you their syntax, how they create their tables. Notice they create node tables, they create edge tables. There is a whole slew of queries here, as you can see. These queries are used like this, so you insert into these different node tables and these different edge tables. You know, you can see the structure of how they do it. For example, they use this $sign in front of these IDs. So it's quite involved. I just want to say a couple of words about how SQL Server creates its graph table and what they look like. So if you look here, I created this document where I show you a couple of things about SQL Server graph database. So notice that it's still the nodes and edges like you've seen before, but they create columns here, as you can see, that has a prefix of a $sign. So you have a node ID, that is the first, it's like a primary key on this node table. And then that's system generated. And then you can see you have a reference to a from and a to. And these are the relationship between the nodes. And notice the prefix with a $sign as well. And if you look down at this table, here's an example in plain text. And then Alice is a person, Bob is a person, company X is an organization, and some created date. And notice here that the node ID is system generated, unique identifier. The name is the custom column for that node name. The type is the type of classification, so person, organization, etc. Now, if you look at the simplified view, here is what a representation will look like. So you have an edge ID, you have a from ID, and a to ID, prefixed with a $sign. And if you look down here, you can read this on your own. But what I want to point out is that behind the scenes, SQL Server doesn't use this representation like ints. It uses JSON. So if you look here, what is really showing up in the from ID and to ID is of type N varchar, meaning Unicode varchar field that is twice the size of a regular varchar. So if you look here, the edge ID is a small fragments of JSON that is stored. And the from ID, same thing. You can see here the table, the schema, etc. And the to ID is the same thing. So source and destination, basically. But notice it's stored as a JSON fragment. If you look here, you can see that it's an nvarchar column. These are the names of the columns. There's a $sign in front of it. So that makes it a little more tricky to understand, I think. But here is a script you can use in order to create this table that you're looking at here. So I just want to point that out. And also, if you want more in-depth analysis here, you can go right here to this website, which is part of the Microsoft Learning. As you can see, the Ignite. Here are some of the functions that you can use in SQL Server for a graph database. So I created this document here. You can see how you can convert SQL Server graph database, that example I just looked at on their website, to a DuckDB using this DuckPGQ extension, the community extension. So I'm using version 1.4.1 in DuckDB. And you can see here that this extension brings, graph queries availability to DuckDB users as well using the SQL 2023 standard. Now, here is a couple of things that kind of contrast the way SQL Server does it and DuckDB does it. Notice that when you create a table, an entity or node table, you list it as a node like this, and then you create these edge tables like using the words like likes and edge. Now, if you do the same thing in DuckDB, you create a regular table. You don't specify it as a node table. So as you can see, you create a regular table with an ID, a primary key, and a name. And then you create another table called a likes. So at this point, there are just two tables. Here, they're already structured into a graph structure with a node and an edge table. So this is the connector table because a person likes whatever, a restaurant or what have you. Here, you simply create the tables like this. So it's a regular table. So what is the next step though? How do you make it into a graph table in DuckDB? Well, what you do is you create what's called a property graph structure and give it a name like this. And this vertex keyword is the same as a node. Okay, so these are the node tables. Okay, the entity tables, if you will. So you have person, restaurant, and city. Okay, so a person likes. So notice here you set up the edge structure. Here you can see what SQL Server did. It created this edge structure like this. You create a graph over the regular tables in DuckDB. So that's how you structure this by doing it this way. So you can set up connectors like likes, friend of, etc., etc., etc. You have a source and a destination, and you need to have keys for it so it can find, the structures. So here's the person ID, reference the person. So that's the node. And here's a restaurant ID, reference the restaurant, which is the node up here. There's also a friend of, so a person can be a friend of another person, which you call person, refers to that person ID. So one person to another person type of thing, and that's it. You get the idea. So here you can see the vertices are the nodes, and the edges are the relationships, as you can see here, if you read this piece here. Okay, so in regular databases, you relate to this via primary keys and foreign keys, right? This is the edge table structure for SQL Server when you insert a record. Notice you insert into the edge table, and here is just what you're querying to put in there. But notice you're querying it in like an ID like this with a $sign. So it's kind of cryptic, I think. I don't think it's easy to understand it that way. Notice what DuckDB does. Insert it directly into them like this. And you just put the relationships like this. So a person ID, the restaurant ID, and a rating, you just give them values like this. Now, once you get into the graph syntax, you're going to use keywords like match. Now, you find that in the SQL Server too. If you look at, for example, the pattern matching, you use the match keyword where you take, say, a person P. He likes, meaning using this dash here as like a connector. He likes this restaurant. So you give that an alias R, and likes becomes an alias L. The person's name is John, for example. That way you can connect the person to a restaurant that he likes via the likes connector. So you can also do multi-hop. What does that mean? Well, so one person connects to another person, but you can also say that next person connects to yet another person. Then you're doing a multi-hop. You can determine how many times you're going to hop to. All right, so for example, John's friends, what kind of restaurants do they like? So first you have to find John, and then you have to find who the friends are, and then you got to figure out what restaurants do they like. Well, here's John. So you match John, that is a friend of this second person, this guy, and he likes this restaurant here. So you got a hop here, and you got a hop here. So you got a two-hop kind of thing. So there's two edges, in other words, right? These edges. Actually, I'm sorry. This is the edge, and this is the edge, right? These others are nodes. Okay, so you start getting the idea probably. You can do some other things like, hey, find the shortest path between John and other people. So you have John here. He's a friend of this other person like this, where you start with John, right? This syntax here means one or more hops. So this plus sign makes it almost like a regular expression where you can then find the next, and so forth. So there's no upper limit, in other words, because of this plus. Here, you're specifically saying 2 hops, okay, from 1 to 2. So you basically narrow it down. So it's almost like a regular expression type of things where you do with numbers, like digits. Here, you can use keywords like any shortest. It finds the shortest path among multiple possibilities. You can get into this, and there's a lot to say about this, and I'm no expert in this, but I just want to point out, where you can find this kind of information. And here's another example of a multiple patterns, and not just finding one thing. So it's like this person, or this restaurant. But here you have 2 conditions. So you say this person, and then the edge, he likes this restaurant, which again is located in this city. And the person also, he lives in this city. So here you have 2 conditions basically. And the shared variables P and C ensure that they connect properly. So you can see you comma separate the multiple patterns. All right, so what is the advantage of a DuckPGQ approach? Well, it uses standard SQL. So that's always good using standards. There's no data duplication because, you don't make copies at all. Matching an intuitive way of joining complex joins. Performance, and it's 2023 SQL standard, and it's very flexible. You can switch all kinds of connections. Now, the use cases we saw above: social networks, fraud detection for banks and financial companies, knowledge graphs, supply chains, and network analysis. And here I'm just listing how you get started with this, but we're going to look at this a lot more in detail in a script we're going to be using. Here are some resources. Here you can find the documentation for this DuckPGQ community extension, as well as here. This takes you to the actual page where they describe it. So if you go to the landing page for DuckPGQ here, and it's duckpgq.org, scroll down, you can see you can do how you can use it in Python, in R, etc., or the CLI. But here is what I want to show you. If you look down here, you can explore it across different domains. Here they give you lots of examples, which is really nice. So you can find like a shortest path for social networks, shortest path query, how to find mutual friends, most popular people, etc. And the way you can do this to set this up, just click this button, and notice they give you all the code you need to create this example to test out these queries. So it's very nice. Airline data, this is how you set it up. You can see here you create your edge tables like this and your property graph. And here's the vertex table or the nodes. Most expensive seats on the average, how you structure that based on that setup. And finally, for like financial data, you have these find blocked accounts via transfers, filter high value transfers by time, and setup. As you can see, they created a lot of edge tables here, as you can see. So that's the connector between these nodes, meaning the accounts, the companies, the loan, medium, person. So make sure you study this because this will give you a lot of insight into how you can actually use this. So it's very useful. And the blog post that I'm also referring to in my documents there, it's using this FinBench. So it's based on this DuckDB database, I guess. So read this. This is very informative. Also, there is, if you want to go to the GitHub for this, you can go here and read up some more on this. So anyways, there's a lot of information, and I'm just showing you an introduction to how this one works. Okay, so let's wrap it up with some quick examples of how you can use this. So here you can see I'm opening up my DuckDB CLI. So this is just a shell, meaning the DuckDB CLI. And right now it's version 1.4.1 called Endium, okay? You can use the call command. So it's called start_UI. If you open it from a regular command window, then you can just say DuckDB space -UI, and it will open it as well. So right now I'm inside the CLI, so I can just open it here, and it will open up a web page for me. On that web page, as you can see, I have some notebooks once it loads here. And I created this DuckDB PGQ notebook. So the first thing you need to do, right now I'm working out of memory because I haven't created a fixed database to do this. So what I can do is I can install the DuckPGQ from community by using this command. But since I already have that, run that, it's already installed. So what I want to do instead then is just to load it. So let's load it. And here you can see it loads it. So the first thing we want to do is create these vertex tables, or the nodes tables so-called. So I'm creating a regular table, person, restaurant, and city with some IDs and primary keys, etc. in it. So let's run that. Okay, so that's done. Now we can create edge tables, meaning the relationship tables. Person likes, is a friend of, he lives in the city, whatever, and you use these IDs here. So these are connector tables. So let's run those. Okay, so I ran that. Remember, this example here is based on that SQL Server graph database. So now we're going to do the insert statements you saw here. So you can kind of draw a parallel between them. So here we're going to insert into these nodes table in DuckDB for person, restaurant, and city. So let's run that. Okay, so we ran 3 insert statements. Now we want to insert the data into the edge table. And this is kind of similar to what we're doing here, right? This part. So you can see how much convoluted the SQL Server inserts are with this node ID, with a $sign, etc. It's a little more simple this way, I think. So let's run those inserts. These are the connectors. This is how one person relates to the restaurant and how the rating. You can see 1-1 connectors, and they based on these inserts up here. So you can go back and forth and look at the relationships. He lives in, located in, friend of, etc. So let's run that. Okay, so 5 of those inserts. Now we want to create the property graph. So notice the property graph, we call it social network. Here's our nodes tables, person, restaurant, city. And here's our edge tables, likes, friend of, lives in, located in. So let's run that. Okay, now we're ready to go. We can test it out. So the first query here, we're going to look for some graph pattern. So first we want to find the restaurants that John likes. We want to select the name of the restaurant from the graph table called social network, which is the property graph, right? Since the person's name is John we're looking for, we want to find a restaurant here where John likes the restaurant, right? One thing I should mention too is that when you created the property graph, we created a label like this, likes, friend of. So those are kind of the keywords we use. So for example, located in, lives in, friend of, right? So that's the stuff you can refer to in your links. All right, so this is the restaurants that John likes, the Taco Del, right? All right, the next one is find the restaurants that John's friends like, okay? So now we want to look for what his friends like. Okay, so now we're going to do a hop, right? We're going to find John, which is a friend of this second person that likes this restaurant, okay? So that's what we're doing here. So it looks like John's friends like Ginger and Spice restaurant. So you start getting the idea here. So we'll just move quickly through this. Here, we want to find the people who likes a restaurant in the same city they live. So now you have 2 conditions, right? So if a person likes a restaurant that are located in this city, he also have to live in this city. Okay, so that's the condition. So let's run. And John, Mary, Alice, and Jacob lives in the same cities that likes the restaurant in that same city, in other words. Find the friends of friends of friends. So there's 3 hops here. So we can exclude the cases where relationships loops back. Okay, so it's a one-way street. So now it gets more complicated. So you can see here's the matching. Find a person who's a friend of the second person, which is a friend of the third person, which is a friend of the fourth person. So you get 3 hops here. And here is the filtering. Person 2 cannot equal person 3 and so on. So you don't go backwards. Otherwise, you're getting into this cyclic thing, right? So let's run that and see what happens. Okay, so Jacob he's a friend of Mary, who's a friend of Alice, who's a friend of John. Okay, so you get the idea. So you're getting more complex now with these connectors. Here we want to find all the paths of friends that the shortest path is between John and all the other people. So here we query from the graph, the social network table, using these any shortest keywords, where the person 1, in this case John, is a friend of person 2. But notice you have a plus sign. So that means 1 or more. You keep more and more and more and more friends, right? And when you run that, you're getting John is linked to Mary by 1 hop, right? John is also linked to Alice by 2 hops. So how can you find that out? Well, if you remember going back to the insert statements here, you can see friend of, right? So the person 1 is John. He's the person 1, right? Alice is 3, Mary is 2. So we're looking for combination of 1 to 2, 1 to 3 kind of thing, right? And that's what these insert combinations do. So friend of 1 is linked to 2 and 3 is linked to 1. So if you look down here at this one, you see John is linked to Mary. So there's 1 hop. And John was linked to Alice. So there's 2 hops. That's how you connect those two. And you can also find all restaurants liked by friends within 2 hops. So how do you do that? Well, you match the person who's a friend of. And notice here you go in specific, almost like digits in a regular expression, 1 to 2. So only 2 hops here. And that second person must like this restaurant. So you start with John, and these are the columns we're looking for. So let's run that. And here you see John by friends within 2 hops. The restaurants they like is Ginger and Spice and Noodle Land. Okay, so you can imagine how complex this can get when you have a lot of conditions. And finally then, we look at this last query. Find everybody who lives in the same city, and they all have to like the restaurants in that city, right? So again, the person likes the restaurant, which is located in this city, and the person must live in this city. So when you run that, you can see 4 rows was returned, and John likes Taco Bell, we knew that, and he lives in Bellevue, and the rating was 9, I guess, for Taco Bell. All right, so you get an idea of how to look at these Graph SQL and the DuckDB PGQ extension. So I hope this was interesting, and I hope you like my videos. And if you do, please give me a like and consider subscribing to my channel. That'd be fantastic. Hope you have a great evening, day, wherever you happen to be in the world. And I look forward to see you in the next video. Thank you.